Good evening, here yet again for another volley session of CENG 3325 Structural Analysis. This is going to be part 2 of lecture 23 in the video series, and in this video I'm going to be working through a bit of a long-form example, walking through the force method or applying the force method to a simple beam. And this example is going to show the force method for single degree indeterminacy beams. So we're going to have the following information given. We're going to start with a beam, and this is going to be a continuous beam. So rather than a simply supported or a cantilever or something else, this is going to be a continuous beam. What I mean by a continuous beam, of course, is a beam that continues through multiple spans. So this would be something like an example of a continuous beam would be something like let's say a highway bridge with a set of columns in between the two abutments. That would be a continuous beam, something that goes between multiple spans. And it's going to have dimensions, just for fun to make this interesting. I'm not even going to make it symmetric. This is going to be 12 feet on the left span and 10 feet on the right span. Then the load will be a uniform 2 kips per foot across the top of the beam. A uniform 2 kips per foot across the top of the beam. And we're also given a bit of information about, let's see, let me show first some point labels. This is going to be point A, point B, and point C, no great surprise there. And we are also told a bit about the material property and our cross-sectional properties. So the relevant material property here is the modulus of elasticity, and this is 29,000 KSI. And the moment of inertia I for our strong axis bending is going to be 300 inches to the 4th power. 300 inches to the 4th power. So all this is given, and we want to find the max deflection in the beam. So I want to find the max deflection in this beam. So the problem with this, looking at this, is that this is definitely going to be indeterminate. We have 4 potential unknown forces, and we have 4 unknown forces, and because of the pin and the 2 rollers, we have 4 unknown forces, but we only have 3 equations of equilibrium. So we cannot solve this using statics alone. So let's go and work through a series of steps to apply the force method to this problem. I suggest if this is the first force method video of mine that you're watching, I would suggest that you go back and watch part 1 of this video, as we are going to be applying a lot of the theory we saw in that video. So the first step is going to be just to draw a Freebody diagram of our beam. And this isn't going to be too bad. I'll show the loads on here. I'm going to have a uniform 2 kip per foot load across the top, so 2,000 pounds per foot. Two kips per foot across the top. Then my reactions, I'm going to have a By at the center, an Ax on the left end, an Ay on the left end, and a Cy on the right end. And a Cy on the right end. And our dimensions, of course, those aren't changing. These are going to be 12 foot and 14 foot. So that's our Freebody diagram, and we can see that this is going to be indeterminate, as we've already mentioned. So the second step is going to be determine the degree of indeterminacy, or find the degree of indeterminacy. And so for this particular beam, we have 4 unknowns and 3 equations of equilibrium because this is a single rigid body. So 4 minus 3 equals 1. This is indeterminate to degree 1. Or indeterminate to the 1st degree. And I should probably lump another thing into this step, say find a degree of indeterminacy and redundant force, or redundant support. Or you could also say choose the redundant support. Now, we could use almost any of them. Well, we couldn't use the AX It is tempting to do that one because that would, well, it is kind of tempting to do that one, but that wouldn't really help us because then we'd still have 3 unknown forces in the vertical direction. That really still wouldn't be a statically determinate system. So now I could pick CY, and then I would have a beam that had a support here and a support here, and then a cancel over here. But really, BY makes the most sense. And the reason for that is that once I remove this, if I imagine removing this roller here, that would basically turn this into a simply supported beam. And that's going to make doing the calculations much simpler. So I'm going to pick, I will pick support B as the redundant. So again, if we recall from the previous theory, we're going to have a primary beam and a secondary beam, and if you have more than 2 degrees of determinacy, or 2 or more, you'd have 2 secondary beams or 3 secondary beams, etc. This is indeterminate to the first degree, so we're only going to have 1 secondary beam. And the primary beam is going to have is going to show the beam with the support removed, the redundant support removed, and the real loads, while the secondary beam will show the real loads removed with a unit load applied at the direction and location of our removed support. So step 3 then will be to analyze the primary beam. And as a reminder, this primary beam is actual beam, real loads, with redundant support removed. With the redundant removed. So let's consider this. Once I take away that, I'm going to go ahead and ignore the x force here like I usually do. We have no forces in the x direction, so that's clearly going to be equal to 0. And so, once you remove that middle support, I just have a very simple system. I have a uniformly distributed, simply supported beam, or a simply supported beam with a constant uniformly distributed load on it. 2 kips per foot, and we would have loads of 20 kips and 20 kips, or reactions of 20 kips and 20 kips on both sides. 20 kips and 20 kips, and then a deflected shape just along here. A deflected shape like so. And we are interested in finding the deflection at the location where we removed the support. So I'm going to say we're looking right here at that would be our delta BO, capital delta BO. That's going to be the deflection at point B from the primary loading. And in terms of dimensions that we saw previously, this is going to be 12 feet and 10 feet. So we have a simply supported beam and we have a uniform load on it, and we basically need to find the deflection at this point here. Now we could do this a number of ways. We could go and do all this by integration, but the nice thing about this being a simply supported beam, and the reason I chose to use that as redundant, is that this is a form, a very common shape, or a very common support condition, which means I don't need to rederive the formulas. I mean, we've already looked through how to derive deflection formulas. I think at this point in the semester, you can handle anything, essentially any kind of beam with anything within reason. So we could derive that. We could actually derive the deflection at say 12 feet, or derive deflection as a function of x. But the nice thing about this is once we have, because it's a simply supported beam, I can find this form in my load tables or in my beam tables. So from beam tables, I went to a beam table. I went to the ASC Steel Manual, and I looked at their equations, and what I found was again something I could derive, but this problem is going to be long enough. I don't want to work through multiple derivations. So I found that W is a function of x for a beam like this, a uniform load, simply supported beam, looking for a deflection somewhere other than the center. You can use the formula W over x times 24 EI times L to the third minus 3x squared minus 3x squared plus x to the third, where L is the length of the beam and x is the location where you want to know the deflection. Okay? Now, we got to be very careful with our units here, so I'm just going to go ahead and say that L is equal to not just 22 feet, the total length of the beam, but that is equal to 264 inches. Just multiply that by 12. And X, the place that we've removed the load, or removed the support, X is 12 feet, or 144 inches. And then W, also need to convert that. W is, let's see, that is going to be 2 kips per foot, or 1/6 kip per inch, 1/6 of a kip per inch, or 0.167 kips per inch if I do the decimal. So plugging this in, delta X equals 0.167 times 144 for our X divided by 24 times our modulus elasticity of 29,000 KSI times our moment of inertia of 300 inches to the 4th power times L, which is 264 to the 3rd power, 264 to the 3rd power, let's see, minus 202 times 264, the length again, times X, where we want the deflection, 144 quantity squared, and then plus 144 to the 3rd power. And when you go and calculate all of this, you will find that this equals 1.20 inches. So this is delta at X, or also delta BD. This is, again, this delta of X function is something I found in a beam table that will give the, for a beam like this, the support conditions and this type of load. And again, you do have to make sure you use just the right equation if you're using this method. You have to make sure you're using a equation that reflects both your support conditions and the type of loading that you have. But anyway, when I did, that's just plug and chug. That's just plugging and chugging here. And so we now have our delta BO. This is, again, or if you want to call it B naught, this is the deflection at point B from the real loading, with the deflection at point B from the real loading with the middle support removed. So again, one way to think of this is without roller B, if I just came along, if this was a bridge and I came along and, blew up the middle support there, without B, without support B, the beam will deflect 20 inches at B, or sorry, 1.2 inches at B. Of course, now something I do see when I look at this, I wonder, wait a minute, if this is only 1.2 inches, I would wonder what is the point of that middle support actually entirely. That's really not that bad a deflection on that long of a span, although I would have to do the calculations. Actually, let's do that really quick. I'm curious, what is that? If I convert that 22 to 2 inches, again, times 12, so 1.2 over 264, does that meet our 1 over 240? Not quite. So it may actually exceed a deflection limit, depending on what kind of deflection limit you're using for your beams. But really, that's not too bad of a deflection. I'm not sure I would bother building a middle pier. Although maybe that's for maybe they did that for strength rather than for, maybe they had that middle support for strength rather than for deflection. Or maybe that middle pier exists because this is a contrived example. I guess we'll never know. So, step 4 is going to be to analyze the secondary beam. And again here, I'm going to use an equation from our beam tables. Analyze the secondary beam. And again, the secondary beam is a beam with the real support, the real geometry, but again, the support removed, but the real loads have been removed. So backing up, let me just rephrase this. The secondary beam, again, is the beam with the real loads removed and a unit virtual load applied at the location where you removed the redundant. So here, we're going to apply a 1 kip load at the location of B. And this would be 12 feet from the left and 10 feet from the right. Notice the the uniform load has decreased, or not decreased, has vanished. We removed it. So I could go and solve for the reactions and things like that, but I don't think I'm going to bother because I'm just going to use the formula again. Now, I found something in a table. The form I found was for a place where you wanted to know where you were dealing with a point load somewhere other than the center, so some point load P here, somewhere at the center, and you wanted to know the deflection at that point. And the table in the equation in the steel manual uses variables a and b, where a is the distance from the left end, b is the distance from the right end, and length L is the overall length of the beam. So the formula I have, which I'll write here, is that delta at A, the deflection at A, is going to be P A squared B squared divided by 3EIL. So I'm just need to put in my A, my B, and my L. Actually, let me write a lowercase l there so it matches. And the rest is just plug and chug. So that will be, the P is 1 kip. A is going to be 144 inches, quantity squared. B is going to be 120 inches squared. 3 then times 29,000. KSI times our I, or moment of inertia, of 300 inches to the 4th power, times our length of 22 inches. Times our length of 22 inches, and I find the deflection from this unit load at A is 0.0433 inches. And I really don't want to use this because this is just something I found in a table of formulas. What this really is, though, for our purposes, is lowercase delta bb. Again, this is the deflection at B from a unit load at B. So the next step, 5, will be to balance the deflections. So what do I know so far? Well, I know a few things. I know that without that middle support, at B, this thing is going to bend down 1.2 inches. I also know that if I apply a 1 kip load upward at B, it's going to cause it to move upward 0.043 inches. And so, because I know there's a linear relationship between load and deflection as long as deflection is small, again, as long as deflection is small, there is a linear relationship between load and deflection. If I double the load, I double the deflection. If I triple the load, I triple the deflection, etc. So, if I know that this load without the support will cause it to bend down 1.2 inches, I know in turn that if this was acting alone, if the reaction at B could somehow act alone, it would have to cause equal and opposite displacements. So basically, the reaction at B would have to cause an upward displacement of 1.2 inches. Or I can just use the equation of balance I've seen before. Delta BO, capital delta BO, plus BY, the actual reaction at B, times delta BB, the deflection from the unit load at B, is equal to 0, and BY is then equal to negative delta B naught, or BO, divided by lowercase delta BB. And that is negative 1.20 divided by 0.0433. And I find that my BY is 27.68 kips. So I now know the reaction there. So finally, my last step, which can be a bit long, is going to be to analyze the statically determinate system. And after this, we're really basically done with the force method, but I'll continue working through the problem until I solve it, just so you can see what we would do. And again, once you've removed once you've removed that redundant reaction, that redundant support, it's just another load in the structure. So what I mean by this is what your beam now becomes. You can analyze it as a simply supported beam with a distributed load. We can analyze it as a simply supported beam with a distributed load of 2 kips per foot, a distributed load of 2 kips per foot, and instead of a reaction, an upward load of, let's put it on the other side here, of 27.683 kips. The reaction that we found using the force method. And we'll have 12 feet and 10 feet here. And then we'd have an AY and a CY. And so if you balance moments, I don't necessarily want to work through all of the math, but I'll just go through the steps. So if I balance the moments and check, etc., again, just basic statics, I have a beam like this, and of course I also have a CY here. Let me show you that arrow, I guess. I found that CY is equal to 6.90 kips, and AY is equal to 9.417 kips. Is equal to 9.417 kips. So, next, I'm going to keep working through this. Let me draw the Freebody diagram of the combined thing. So the final Freebody diagram of this will have my distributed load of 2 kips per foot across the top, a reaction on the left-hand side of 9.417 kips, on the right-hand side of 6.90 kips, and a middle reaction of 27.683 kips. Of 27.683 kips, and again 12 feet and 10 feet. Our dimensions. So I'm just going to do this by integration. Now, I could go and analyze both spans, but I think it's pretty intuitive. I can use just some basic engineering common sense to say that for a uniform beam like this, if I ever have a longer span with a uniform beam, I can pretty much guarantee that the max deflection is going to occur somewhere on the left-hand side or on the left span. So I don't necessarily now for time's sake, brevity's sake, I'm going to ignore this span right here and just solve for the shear moment and deflection on this span here instead of doing the full piecewise function. If you wanted to check it, you could, but I think on a longer span it's pretty intuitive that the max deflection there's really no way the max deflection is going to be in this span. The max deflection has to be somewhere in the longest span, especially because the load was uniform. If this was a non-uniform load, then we wouldn't be able to make that assumption, but because it is a uniform load, the max deflection has to be somewhere in the left span. So max deflection will be somewhere in the left span. Left span somewhere. So I will find functions only for the left-hand side or for the left span. So first of all, let's just go through the deflection by integration. Very simple method. So W of x, our load, we already have that. That is 2 kips per foot. V of x then is going to be the integral of W of x dx, and that will be, well, actually it's the negative integral of W of x dx, and that's going to be negative 2x plus c1. Now I do need a boundary condition, and the boundary condition is that the shear at x equals 0 is equal to 9.417 kips, this one here. And if I put in 0 and 9.417, that means that C1 is equal to 9.417 kips. So I have that, 9.417 kips. Next, I can find the moment as a function of x. The moment as a function of x is going to be the integral of v of x dx, and when you take the integral, you'll find that it is negative x squared plus 9.417x plus C2. And our boundary condition? Well, I know the moment should be 0 at the left end of the beam because it's a pin support. The boundary condition, m at x equals 0 is 0. M at x equals 0 is 0, and because of that, here, m at x equals 0 is 0, so that leads us to C2 being equal to 0. So I now know that m as a function of x is going to be just negative x squared plus 9.417x. And when I get the slope, theta, theta as a function of x is going to be 1 over EI times the integral of m of x dx, and that will come to, I'm just going to leave the 1 over EI out right now, 1 over EI times negative x to the third over 3 when you integrate the previous m of x function, plus 4.708 x squared plus C3. And then y of x, as it looks like a lambda, y as a function of x is going to be equal to the integral of theta as a function of x dx. And also have that 1 over EI there. And that will be times, so we just have that C3, and we integrate that 1 over EI times negative 0.0833 x to the fourth plus 1.569 x to the third plus C3x plus C4. Then, first boundary condition I can use, y at x equals 12, actually I'm going to do x equals 0 first. X equals 0 is 0. Why is this? Well, again, it is a pin support, so the left-hand side of the beam, it's not going to be deflecting any. It will be rotating, but it will not be deflecting. So when you do that, if you put 0 in for this and 0 in for y, you will find that C4 has to be equal to 0, so that one just drops away. Then I can use another boundary condition, and that is that the y at x equals 12. That also has to be equal to 0. So even though on this beam here, I didn't show it, I basically removed it as a support, in reality, it still is a true support. It's not actually going to deflect at all there. So I'm going to say that the deflection there, the vertical deflection there, has to be equal to 0. And when you do that, you'll find if you set up 0 equals 1 over EI times negative 0.0833 times 12 to the fourth power plus 1.569 x to the third power plus C3 times 12. If you solve that for C3, you will find that C3 is equal to negative 82. C3 is equal to negative 82. Then I now have my complete y as a function of x expression. So my deflection equation for first span of beam, or first beam span. And this is that y as a function of x is 1 over EI, 1 over EI times negative 0.0833 x to the fourth plus 1.569 x to the third minus 82x. And I want you to know where this function is maximum, and since this is a constant, I'm just going to maximize this term here. I'm purposely avoiding filling this one out yet because it's going to make the numbers really ugly, and I'm going to need to do some unit conversions anyway. So I'm just going to maximize this. From calculus, I could take the derivative of it and set it equal to 0. I could do any number of ways. I myself solved it graphically and just found I found the x coordinate with the largest value of this function. So even though this is not directly equal to the deflection, we have to include the EI for that. Wherever this inner term is maximum, this whole deflection will be maximum. So I'm going to maximize this expression. And I threw that into a graphing utility, and I found that that term is max at x equals 5.271 feet. So that means we're going to have our maximum deflection at 5.271 feet. So now all you got to do is run through the formula. Although first of all, I have to convert my E. Okay, I do have to be very careful with this. while it might be tempting to use inches and inches to the fourth power for this and KSI for this, the one problem was on this particular one, I can't just go back and convert the length to inches or whatnot. Now I could figure out the exact ratios needed, but I did this whole equation in foot kips, or feet and kips, basically units of feet, and so to try to tease back out the multipliers that I would need to get it back into inches, honestly, unless I carried the units through, all the way through, is probably just not worth it. The path of least resistance, once I already have equations with these ugly, with coefficients these ugly, with units that have disappeared, everything's just kind of baked into the constants. At this point, it's just going to be easier to convert my E and I to feet rather than trying to convert these back to inches. I could have done this with inches, but I would have ended up with some really large numbers, and I was trying to avoid working with some really large numbers. But anyway, let's just go ahead and finish this out. E is going to be equal to 29,000 KSI, which when converted to square feet, or converted to feet, is going to be 4.176 times 10 to the 6th KSF, kips per square feet. And I is equal to 300 inches to the fourth power, or it is also equal to, what is that, 0.0145 feet to the fourth power. So, if you go and say, okay, well, y, we want to know the y at 5.271 feet, and that will be 1 over 29,000. Again, just plugging and chugging at this point. 29,000 times 300 times negative 0.0833 times our distance, 5.217 or 271. 5.271 to the fourth power plus 1.569 times 5.271 to the third power minus 82 times 5.271. And when I did that, I found a deflection equal to negative 0.0042 feet, or 442 feet. And this would be negative downwards for this particular equation. Or I found also that it is, if you multiply by 12, you'll find that this is equal to negative 0.053 inches. Or I could also just say that the max deflection in this beam is going to be 0.053 inches. 0.053 inches. And while that does seem very small for a deflection, it is small for a deflection, but remember we discussed previously, or mentioned previously, that I was quite surprised they would even bother putting in a middle support if the deflection was only an inch on a 22-foot span anyway. So, although of course, again, this was a bit of a contrived example. So, also though, it is kind of neat to look at the relative ratios of this. Without the middle support, we had a deflection of, what was that, of 1.2 inches, and with the middle support, we'll have a max deflection though of 0.053. So 1.2 over 0.053. The deflection is 22 times higher with without the support than with the middle support. And really the reason for this is because while deflection and load have a linear relationship, deflection and span do not. If you look back to these equations here, for example, look at this equation here with span and relating to deflection. Deflection tends to increase with a third power of length of the beam. So deflection tends to increase with a third power of the length of the beam, or in some cases even fourth power, well, depending. Well, actually, no, third power primarily. So, no, I should back up. Sorry about that. If there's an x here, that's length of the fourth power. Yes, I was wrong about that. Or it was right the first time, depending on what you want to say. Deflection tends to increase with a fourth power of length. So if you double your length while keeping stiffness the same, if you double your length, you will increase your deflection by a factor of 16. So that is the importance or the power of adding middle support like that, because you drop I've dropped the span length from 22 feet to 12 feet and 10 feet. Now ideally it would be right in the middle, but maybe there's something here that I can't put, or maybe there's something that I can't fit here, or something. Maybe there's something in the way preventing me from putting that, something in the way that can't be removed that's preventing me from putting it right at the center. Or maybe there are other considerations involved. That's always a possibility. Okay, I hope you found this example illuminating. Again, I just wanted to work through a long-form example of applying the method, applying the force method. I keep wanting to say the method of sections, of applying the force method to a beam of single degree, or a beam with a single degree static indeterminacy. So indeterminate to the first degree beam using the force method. All right, that'll do it. Thank you for watching. Let me know if you have any questions. Thank you for, I hope you've enjoyed this. Hope you've learned a few things here and there. Hope this will pick up. Hopefully this will serve useful in my class or others. I'll see you all next time. And as always, thank you.